Today's topic is refraction. Now, refraction, it's a very important property of light, a very important phenomenon or process related to light. So it is somewhat similar to reflection. So previously you have learnt about reflection of light from a mirror, from a smooth reflecting surface called as mirror. So reflection obeys laws of reflection. The same way refraction is another phenomenon. Now what is refraction? Refraction, it's a, firstly we have the definition here in the syllabus. Definition means simply complete meaning of some phenomenon or some property or something. Some complete meaning is given in simple words. That is called as definition. So what is the definition of refraction? So the definition of refraction or the complete meaning of refraction, in simple words it can be understood like this. It's actually a 2 marks question, a very short answer question, 2 marks. Just one definition, just 3 to 4 lines it will be consisting of. But what is this? In a simple manner it can be understood. Refraction simply means bending of light. Now take light or a light ray. So what is light ray? Light, we have seen that light is a form of energy. Light actually is given out from a source. It will be coming from a source of light. A source of light, simple example of a source of light is electric bulb, a candle, a burning candle. All these objects like electric bulb, burning candle, sun, they give out light or light energy. Now this light energy actually we have learned that it travels in a straight line. Now this straight line along which light energy is traveling, or the light energy which is going exactly along such a thin straight line path, itself is called as a light ray. It is simply called as a light ray. Now whatever light we see, for example we have some electric bulb here. So this is an electric bulb. So it gives off lot of light. This way it's giving out lot of light. Now this large amount of light actually it consists of a large number of light rays actually this way. A large number of light rays this way. So a very large number of light rays or a group of light rays is simply called as a beam of light. A beam of light. It is simply called as a beam of light. So in such a beam of light we have a large number of light rays. Any such one light ray, if you observe the properties or behavior shown by one light ray, the same way even the behavior of other light rays in the beam can be easily understood. Almost the same way all the light rays will be behaving. Now consider one such light ray. Now this light ray, when it passes from one transparent medium into another transparent medium, supposing we have one transparent medium here, this is one transparent medium. What is an example of what is a transparent medium? Any medium through which we can see, or any material or any substance through which we can see. Simple example of substance through which we can see, or we can see other objects through that substance, is nothing but a glass plate. A glass plate is a transparent medium. Similar example, another simple example of a transparent medium is water. Through water also we can see other objects. Now another even more simple example than glass, water is air. Surrounding us, all of us are present inside air only. So above the ground air is present. That air only helps us in breathing. We breathe in air. Without air we cannot live actually. So air is also transparent. The reason is through air we can see all the objects around us. Through glass also we can see all these objects are called as transparent objects. Now the important thing is we can see through such media like glass, water, air only because light can pass through them. A light ray, when it is incident on a transparent medium, easily it can pass through the transparent medium. So this gives another simple meaning of a transparent medium. Any medium or any substance or any material through which we can see or through which light can pass is called as a transparent medium. Now when light is passing from one transparent medium into another transparent medium, it is found that light bends. Supposing it's initially it's going in one transparent medium, it's going like this, the light ray is going like this. Supposing suddenly at the beyond this point another medium is there, then what happens is the light ray will be actually bending this way. This way light ray will be bending. So this bending of light, when it passes from one transparent medium into another, up to here one transparent medium is there, say glass is there, beyond the glass some air is there or water is there, then exactly at the point which is actually separating the two media, this is the point which is actually said to be separating the two media. It means on this side, left side of the point, glass medium is there, right side of the point some other medium, water medium or air medium is there. That point is called as point of separation of the two media. Exactly at the point of separation of the two media, light ray will not be going in the same direction, it will be just bending and takes a different direction. This bending of light, when light is passing from one transparent medium into another, this is the first transparent medium, this can be called as second transparent medium, on either side of this dashed line which I am drawing here. This phenomenon itself is called as bending of light. So the meaning of refraction is very simple. Refraction is the bending of light traveling from one transparent medium into another transparent medium, one transparent medium into another transparent medium, and this bending occurs exactly at the point separating the two media. So now consider another simple example. So this is a very simple example which is actually nothing but gives a complete meaning of refraction, and from this a very important quantity is defined called as refractive index, and also very important law is also obtained from this called as Snell's law of refraction. So refraction is already we have seen what it is a bending of light when light is traveling from one transparent medium into another transparent medium occurring at the point separating the two media. Now here this is the light ray, PO is a light ray which is actually initially traveling in air medium. So this is the air medium. Now just below the air medium we have a glass block. Just observe here, this is a glass block. It is a rectangular glass block. This is a rectangle, almost in the shape of a rectangle. The glass block, a glass block, heavy glass block is taken. Glass, we know that it's transparent. So this is transparent medium which we have taken here. And next, above the glass block, what is there? Only air is there. So air also, we know that it is a transparent medium. So light can pass through air as well as glass. Now light is made to pass from air into glass. So PO is the light ray which is initially present, which is initially passing through or traveling through air this way. PO is the light ray. Now this light ray is actually incident on the, it is falling. Incident means falling. You have learnt in reflection. So previous topic reflection, you have learnt incident ray, reflected ray, right, like that. So like that here also we are considering one such ray which is actually incident. Incident means falling on the surface SS dash. SS dash denotes the surface of the glass block or glass medium. So PO is the light ray which is incident on the surface SS dash of the glass block. Exactly at the point O it is incident. So PO is called as incident ray as usual. Just like in reflection, you have learnt about incident ray. Light ray which is falling on a mirror is called incident ray. Like that, this is a light ray which is falling on the surface of a glass block. Surface of a glass block, a transparent medium. Glass block is a transparent medium here. So this is the incident ray. Now once it is incident on the glass block, immediately it is found that light can, already we know that from the definition of transparent medium, light ray can travel inside the transparent medium. So this light ray now passes or travels inside the glass medium. Now O is the point separating the air and glass. The reason is above the point O, a point of incidence, we have air medium. This is the air medium. Now observe the cursor compulsorily. So whatever very important point is there, I am just explaining with the cursor, showing the cursor. So from the diagram, in almost everything in the universe, in science and technology, or science and engineering, or science and technology and engineering are nothing but applications of science. Applied science is called as either technology or engineering. So whatever is there in science and technology or science and engineering, anything can be understood by careful observation of the real life situation. Now here we are considering a real life situation just by using, how is a real life situation understood? Just by drawing the diagram of the real life situation. Now this is a very simple diagram of the real life situation where we are considering a glass block placed in air. Simply we are putting the glass block on some surface, and above the glass block we have air. Always air is there everywhere. Now light can be made to pass from air into glass. So just by looking at the diagram, very easily the real life situation, what is happening, can be easily understood. And from such careful observations of real life situations only, great scientists have given great laws. So Snell was another great scientist who has given this very powerful law. Almost many things in optics are explained with the help of the Snell's law of refraction only. Many things. Many complicated things will become very simple just by applying this Snell's law of refraction. So many such powerful laws were given by great scientists just by careful observation. This is also one such law. So when the light ray, now PO, is incident at the point O, now it is entering into the glass medium. We know that glass is transparent, so light can pass through glass. So O is the point separating the two media, air medium above the point O, below the point O is glass medium. Exactly at this point of separation of the two media, it is found that light ray is found to be bending. So instead of going in the same straight direction, now the direction of the incident ray PO, we are just extending it by means of a dashed line. So this is the extension of the incident ray. So this is called as direction of incidence. This is called as direction of incidence. Supposing the light ray is only traveling through air only, then it will go straight line like this, because light travels in straight line path. This is also called as rectilinear propagation of light. This property, the property of light ray, or the property of light to travel in straight lines, is called as rectilinear propagation. So based on rectilinear propagation, it should travel in a straight line path. But that is true only in case of air medium, only in case of single medium. Now what is happening? Medium is changing. So instead of taking the direction of incidence, same incident direction, what is happening is, because of the change in the medium, light now undergoes refraction. So instead of taking the same direction, now what is happening? It is bending. In what way it is bending? Just observe here. Now at the point O, one imaginary perpendicular is considered to the surface S dash. Now this perpendicular drawn exactly at the point O of incidence, which is perpendicular to the surface of the glass, is denoted as NO N dash. It is called as normal to the surface, or normal to the glass block surface. Now it's exactly like the normal which you have learnt in reflection. So similar normal is considered here. The normal here is NO N dash is very important, because the direction of the incident ray or any ray, light ray, the direction of any light ray is actually indicated with the help of the normal NO N dash itself. The same thing actually was done even in previous topic, reflection. Reflection also, the direction of the two rays in reflection, two rays were important. The two rays were incident ray and reflected ray. Their directions are actually indicated with the help of the normal NO N dash itself, with the help of such a normal itself. Now the same thing here is done. The direction of the incident ray, and here instead of reflected ray there is a second ray. Here actually in the diagram it can be shown as, it is actually visible as OQ. OQ is the second ray which is different from the incident ray. Now this OQ is called as refracted ray. Why it is called as refracted ray? It will be coming immediately in the next step itself. So their directions are actually indicated with the help of the normal here. So how they are indicated with the help of the normal? Simply by means of the angle which the incident ray is making with the normal. Just see here, the incident ray, that is PO, is actually making some angle denoted as I here. I stands for, actually it's related to the incident ray, that's why it's denoted as I. So this is called as angle of incidence. Even in reflection also you have learned that angle of incidence will be there. So the direction of each light ray, whether it's incident ray or the refracted ray OQ, their directions are actually indicated with the help of the angle which the light ray makes with the normal NO N dash. So that's the importance of the normal. So that's very important. It has a very important function, the imaginary normal NO N dash. So normal here is nothing but perpendicular. It's an imaginary perpendicular on the surface SS dash, exactly at the point of incidence O. So now consider the direction of the incident ray. It's called incidence direction. Now in the absence of the medium, supposing glass medium is not present, then the light ray just goes straight because of the rectilinear propagation of light. It just goes in the direction of this dashed line, which is the direction of the incident ray itself. But because there is a medium here, glass medium is present here, what is happening is light ray, because the light ray is now undergoing a change in medium. It's actually passing from air medium into glass medium. Because of this change medium, light ray cannot take the incident direction, that is the incidence direction, but it takes a different direction because of the bending occurring at the point O. So this bending itself, we have seen that it's called as refraction. So because of refraction, the light ray is taking a different direction. So that different direction is actually shown as OQ. So this is the light ray after bending, after refraction. That's why OQ is called as refracted ray. Now the angle which the refracted ray is where it is inside the medium, inside the denser medium, inside the medium actually. So actually the medium here, glass medium, is called as a denser medium. Now the reason why it's called as density means heaviness. So glass is much heavier compared to air. So even water is also heavier compared to air. Most of the media are heavy compared to air. Such a medium having higher density is called as denser medium. So glass transparent medium is called as denser transparent medium or denser medium. Now air, the transparent medium air is of lesser density. So lesser density is called as rarer medium. So air is called as rarer. Rarer means density is lesser. Density is lesser. Denser means density is more. Like that it's taken. So less denser medium is simply called as rarer medium. That's the word that is actually used to denote medium having lesser density. So this air is called as rarer medium. Glass is called as denser medium. So once the light ray is actually passing here from air medium into glass medium, that is a rarer medium into the denser medium, what is happening is, already we have seen light ray is bending. So after bending, the direction of the light ray is shown as OQ here. The light ray now, the new light ray, after bent in the new direction, the light ray is present, denoted as OQ. This itself is called as refracted ray. Now the angle which the refracted ray makes with the normal inside the, so refracted ray is where it's inside the glass medium, that is denser medium, it is inside the denser medium. So inside the denser medium, you consider the normal, NON dash, half the normal ON is above the denser medium, that is in the rarer medium it is present, and remaining half of the normal ON dash is actually present in the denser medium. So in the denser medium, whatever the light ray making angle with the normal, that is called as angle of refraction. It is known as R. Same symbols I and R were used even in case of reflection, but there the angles were called as angle of incidence and angle of reflection. But here the phenomenon is refraction. That's why this angle is called as angle of refraction. Now the very important thing is, just observe here, this is the incidence direction. This is incidence direction. It's a single straight line. Just observe here, incidence direction PO extended further by means of this dashed line. It's a single straight line because a single incidence direction, this one. Now you take the normal here. Normal is also a single straight line. Normal is also a single straight line. These two lines, incidence direction and the normal NON dash direction, these two lines are intersecting at the point O. Now wherever two lines, straight lines are intersecting, the vertically opposite angles will be exactly equal at the point of intersection. This is a very important property of angles in case of intersecting straight lines. So you have learned certain very important properties of angles. So for example, vertically opposite angles are equal. In case of two parallel lines and a transversal, you have learned that the corresponding angles are equal, alternating angles are equal. Like the different properties of angles you have learned. Now this is a very simple property, the first property of angles. Vertically opposite angles, when two intersecting straight lines are considered, they will be exactly equal. Now just see here, this is the angle I. Now what is the vertically opposite angle of this angle I? Now just see here, this is the direction, incidence direction, and this is normal direction. So this complete angle here, from here to here, just observe the cursor compulsorily, this complete angle between the incidence direction straight line and the normal straight line, normal which is a straight line, this complete angle is the I. Complete angle is the other angle opposite to the angle I. So this angle is I, means this complete angle will be, total angle will be I. But how is R? You see, R is actually lesser than I, because this total angle is I. Between this dashed line and this dashed line, its total is I. Because of vertically opposite angles equal property, we got this as I. So how is R here? Lesser than I. So what is happening is, if there is no refraction, if there is no bending of light, the light ray PO would have gone just straight in this incidence direction. Then this angle and this angle will be equal. But now what is happening? The light ray is bending in such a way that it is bending. You see in what direction it's bending. Instead of going straight, the light ray is bending towards the normal. The light ray is bending towards the normal. This is very important property. It is actually called as one special law of refraction. This is actually one simple basic law of refraction. In the denser medium, in the glass medium, it can be seen that the light ray is bending towards the normal, due to which the angle of refraction, small r, it is actually lesser than this total angle I. This is very important. Angle of refraction, small r, is lesser than I, the angle of incidence. So why it is lesser? The reason is light ray in the denser medium is bending towards the normal. So it is one very important, very simple law of refraction, considered as a law of refraction actually. Though actually it's not, we are not seeing this as separate laws, because here the important law is the Snell's law of refraction. This is actually a big question. It carries almost from 3 to 5 marks. It's a very, very important question. It carries from 3 marks to 5 marks also. 3 marks, 4 marks and even 5 marks. But mostly it's given for 3 to 4 marks. So it's sometimes called as Snell's law of refraction, sometimes it's called as definition of refractive index. Both are almost same. We can immediately see this a little later. Just a moment please, here when some extra line has come. I'll just erase it. Now it's okay. Okay. So how is R here? Clearly R is lesser than I, or I, the angle of incidence is greater than the angle of refraction. That's what is happening here. So now so all the things here we are able to understand from the diagram, which is actually the representation, simplest representation of the reality. This is what really happens when a light ray is actually passing through from air into glass. So from the diagram everything can be understood very clearly. This is how scientists have given us a method to understand what is happening inside a medium when light is actually passing through the medium. Such diagrams always, scientific diagrams are very simple. They just consist of simple lines, very, very simple lines which show what is really happening in that particular situation, in that particular process, or in that particular phenomenon. So now whatever things we are seeing here are simple, nowhere any complication is there. So in the diagram, many details are there in the diagram. So the important things, important terms that are actually related, or important new terms, new words that are actually related to this particular diagram are like this. We have the incident ray, PO. So what is PO here? I'll just write them in short. So PO is what here? The incident ray. And next important thing is the normal we have seen. NO N dash is the normal. Next, what is OQ here? The refracted ray. And next, two more very important things. One is the angle of incidence. So I is what here? Simply the angle of incidence. So angle of incidence. So that's the name for the angle I. And next important thing is the angle of refraction. So these are the various terms that we have seen in this phenomenon of refraction. So this diagram is actually useful not just for the what I said in the 3 marks and 4 marks answer of refractive index and Snell's law of refraction. This is also very useful to understand the actual definition of refraction itself. So in both cases it is actually useful. But refraction carries only 2 marks because of the many details present in the diagram. Actually the diagram need not be drawn for this. It's useful only for the sake of understanding the definition of refraction. So the diagram is mainly actually related to this particular topic itself. So these are the main terms that are present here: angle of incidence and then angle of refraction. Now one important thing here is, here where is the angle of incidence considered here in the diagram? It's actually considered in the air medium. Already we have seen that it is air has less density, glass has more density. Because of higher density, glass is called as denser medium. Because of lower density of air, it's called as rarer medium. So here important thing here is angle of incidence. It is also called as angle in the rarer medium. So that's the another very important thing that is useful here. Angle in rarer medium. So this is another new name for the angle I. It's not just called as angle of incidence. It's also called as angle in the rarer medium. Now this so this, which is the rarer medium here? That is considered air. So this can also be called as angle in air. Also it can be called as angle in air. But rarer medium need not be always air. It can be anything. It can be any medium that can be considered here. Actually any medium whose density is lesser than glass. For example, water density is less than glass. Kerosene also, it's also transparent medium. Kerosene oil, it's also transparent medium. Its density is also lesser than that of glass. So any such medium also can be considered here. So if air is considered, then only it's called as angle in air. Otherwise in general it's called as angle in the rarer medium. So or in still simpler words, it can be called as angle of incidence. So from the word incidence only I is actually taken. So now But I, though it's actually coming from the word incidence, most of the textbooks don't use this as I as angle of incidence. It is simply called as angle in the rear medium. Now the general symbol for any angle is theta. Theta is actually taken as the general symbol for angle. Angle means it can have different values. Already you have seen, you have learnt in geometry that right angle is 90 degrees. Next, lesser than 90 degrees is 45 degrees, 50 degrees. These are different values of the angles. Whatever be the value, the general symbol for angle is a very simple symbol that is actually commonly used is theta. So because this angle is the angle in the rear medium, this is also denoted as theta rear. So it is also denoted as theta rear. Now the next important quantity here or term that is used, various terms, among the various terms is the angle of refraction. So small r is what here? Angle of refraction. Now this angle of refraction also, so I'll just write the full word. I'm just writing roughly now. Later I'll give little time for taking the running notes. How to write the running notes I'll explain. Then I'll make these words more clear. Now just for the sake of understanding, I'm writing them, and to save some time, to avoid wastage of time, to reduce the time, I'm just writing them in faster. Quickly I'm writing. So angle of refraction. So the angle of refraction is actually considered in which medium? Glass medium. So this can also be called as angle in glass or angle in the denser medium. So this can also be called as what? Angle in the denser medium. So many textbooks actually use this word, actually this name actually, instead of angle of refraction they use it as angle in denser medium. So whether it's angle of refraction or angle of incidence, always it's nothing but the angle made by the light ray with the normal. So angle in the rear medium means angle made by the light ray with the normal only in that particular medium. So again, angle of incidence means angle of incidence with the normal. All the details need not be mentioned. It's just understood that angle of incidence means angle between the light ray and the normal. The same way here also, angle in the rear medium means it's the angle made by the light ray in the rear medium with the normal again. That's the, so in short it's called as angle in the rear medium. The same way here, angle of refraction is called as what? Angle in denser medium. So the symbol for this is theta denser. Theta denser. Theta DEN or DENS it can be written. Anyway it can be written theta denser. So this is the terminology of this particular diagram. The terminology is nothing but collection of different new terms, scientific terms, or the terms related to this particular situation. So 4 or 5 new terms are there. All of them are very useful in the actual definition of the refractive index and the Snell's law of which is also called as Snell's law of refraction statement. So both are almost similar. Now what is the actual definition of the refractive index, or what is the actual definition or statement of this Snell's law of refraction? Now this can be understood from the diagram here. Now refractive index is a very new quantity that is defined, which actually tells about the refraction that is actually occurring. Now the refraction that is actually occurring, why light is bending? Because light is actually, as it is traveling, it is actually experiencing a change in the medium. So initially it was actually traveling through air, next it's going into the medium. Because of this change in medium, light is actually bending exactly at the point separating the two media. So why light is bending means, in simple words, because medium is changing. Then the reason is, already we have seen this also earlier, why when the medium is changing light has to bend. Why should the light bend when the medium is changing? The reason for this also we have seen earlier. When the medium is changing, velocity of light is changing. Because of this change in velocity of light, what is happening is bending of light is actually occurring. So that is found to be the final reason for the bending of light. Bending of light, scientifically it has been proved that occurs mainly because of the change in the velocity of light. Always when light is traveling in a particular medium, it travels with a particular constant velocity. For example, in air, velocity of light in air is fixed value. Air or even vacuum also. Air and vacuum behave the same way with respect to traveling of light. Velocity of light in air or vacuum is 3 into 10 power 8 meters per second. 3 into 10 power 8 meters per second. This velocity of light in air, it has a fixed value. Like that in glass, its value is 2 into 10 power 8 meters per second. Velocity of light in glass is found to be, denser medium it is found to be lesser. Light travels at a lesser speed or lesser velocity. speed and velocity are almost same, but for velocity direction is considered taken as a vector quantity. Direction is present for velocity. For speed direction is not considered, only it has only value or magnitude. What is the magnitude of velocity of light here? In glass, 2 into 10 power 8 meters per second. Or speed is said to be, speed and velocity only magnitude will be same, but velocity one extra quantity will be there, one extra property will be there, direction also will be there. What is the speed of light in air? 3 into 10 power 8 meters per second, or magnitude of velocity is the same, 3 into 10 power 8 meters per second. In glass, its value is what? 2 into 10 power 8 meters per second. So like that, always in a given medium it travels with a particular velocity. Because of this change in velocity, it is proved that bending or refraction will be occurring. That's found to be the scientific reason behind the refraction of light or bending of light. So now, more refraction is occurring means more bending. So a quantity has been defined. It is denoted by the symbol n. It is simply denoted by the symbol n. A quantity has been defined which is denoted by symbol n, simply called as refractive index, which tells about the amount of refraction occurring. So it has been defined in such a way that if n is more for a given pair of media, for example, we are taking a pair of denser and rarer medium, for example, glass and air or glass and kerosene, like that. For a particular pair of media, pair means two media we are taking, n will be having a fixed value. It's defined in such a way that n is higher means more refraction will be occurring. That way, it's a constant which tells about the refraction. That's why it's called as constant of refraction or index of refraction, or simply it's called refractive index. Refractive index means some constant related to refraction. So it's called as refractive constant or refractive index. Anyway, it has been given different names. So simplest word that is used throughout the world is refractive index, or refractive constant also it can be called. So how the refractive index has been defined, that's the very thing, first definition which you have to see here. Now refractive index, how it is defined? Now its definition is obtained like this. Now for example, light is bending more. Imagine that in the denser medium light is bending more amount of refraction is taking place. How can more amount of refraction? Why bending is taking place? Because of change in velocity of light. So velocity of light, what is happening? Here in air, velocity of light is actually very high, because in a rarer medium, light is found to travel at high speed. In a denser, it's just like human beings. For example, air density is very less, so we can walk fast in air. But inside water, how can we walk? How will we are walking? Water is very dense, so it's very difficult to walk in water. The same way, waves also will be moving like that. In a denser medium, waves will travel slowly, just like human beings. Light also is found to be having wave nature. Light travels in the form of waves. This many of you have learned earlier in certain topics. So light travels in the form of waves, like sound also travels in the form of waves. So in a denser medium, they travel slowly. So what is happening is velocity of light in denser medium is changing. We have learned that, we have seen that it is decreasing. So more change means velocity of light is changing more amount is decreasing means refraction will also be more. So here, if the velocity of light in denser medium is very less, that means it's becoming very less. By large amount it's decreasing means bending, refraction also will be more. So the refractive index will be higher. We know that refractive index has been defined in what way? In such a way that if refraction is more, refractive index also will be more. That way it has been exactly defined. So when is refraction more? In the denser medium, velocity of light should be less. It should become very less. Then because of the large amount of decrease in the velocity of light, large amount of bending will be occurring. So refractive index will be more. So refractive index is somewhat inversely related. It is how it is related? It is inversely related to the velocity of light in the denser medium. So velocity of light in the denser medium. So in a denser medium like glass, what is happening is velocity of light is decreasing. If it's decreasing to very low value, it means if velocity of light is very low, refractive index will be very high. That way it is said to be somewhat inversely related to the velocity of light in the denser medium. Now the same way, what about the velocity of light in the rarer medium? In the rarer medium, we have seen that it is very high compared to the denser medium. So this velocity of light in the rarer medium is high. Now if it is very high value, then what is happening? When it's entering into the glass medium, it is decreasing. So for example, we have taken a particular rarer medium here. So velocity of light is very high. So from that very high value, it's decreasing to this particular low value. Now if we take still rarer medium where velocity of light is even higher than this. For example, initially we are taking the rarer medium as air. So its value is say 3 to 10 power 8 meters per second. Now still take, if possible, try to take even rarer medium than air. Even rarer means it will be even higher. Instead of 3 to 10 power 8, it will become 4 into 10 power 8 meters per second. So then what is happening is from 4, its value will be decreasing to the same value in the glass medium. Its value is already, we have seen, it's 2 into 10 power 8. So from 4 to 2 it's decreasing. Earlier it decreased from 3 to 2, now it's decreasing from 4 to 2. So more decrease in velocity of light, more change in velocity of light, more refraction. More refraction means refractive index will be higher. So that means that easily, just see here, if velocity of light in the rarer medium is higher, refractive index is also higher. So it is directly related. It is directly related to the velocity of light in the rarer medium, and it is inversely related to the velocity of light in the denser medium. Due to this reason, refractive index is defined in a simple manner in terms of velocities of light in the rarer medium and denser medium. How it has been defined, just see here, velocity of light in the rarer medium by velocity of light in the denser medium. See here, now it's really depending exactly as we have seen. Velocity, refractive index, velocity of light in the rarer medium is higher, refractive index will also be higher. Just now we have seen velocity of light in the denser medium is lower, refractive index will be higher. So how refractive index is depending on velocity of light in the rarer medium directly, and how it's related to denser medium velocity inversely. Due to this reason, it has been defined exactly like this. Now here, if the numerator is higher, the value will also be higher. It can be seen. If the denominator is lower, then the value will be higher. That's the meaning of this. So any doubt is there, you can just put some values here. For example, you take 100 here, take here 50. 100 by 50 is what? N is equal to 2 we are getting. So you take still lower value. 100 divided by, instead of 50 you take 25. 100 by 25 is what? 4. That way, if the denominator is decreasing, value is increasing. So this is the best way to define. That's why refractive index has been defined like this. So I have explained this in very fast words. So but I did not explain much. Only just 3 or 4 sentences I have explained in this particular diagram. Just observe here this particular diagram. Any doubt is there, just rewind only this part. You just rewind and listen to it once again and try to convince yourself. The important thing is you have to understand on your own, because only once something is understood, then only it can be remembered for a long time. Then only it can be used properly, it can be applied properly to understand even other things. So there is not big explanation here. Just 2 or 3 lines I have explained, only 2 points I have explained. Just once again rewind this and listen to this once again and try to convince yourself that this is the situation. Velocity of light in the rarer medium is higher, refractive index is also higher. Velocity of light in the denser medium is lower. Denser medium is very simple actually. So velocity of light in denser medium is decreasing to a very low value means by large amount velocity of light is decreasing. That means changing. Velocity of light is changing by large amount means more refraction, so more refractive index. So this is very simple to understand. This one inverse relation is very simple. The same way directly also can be understood, but it takes a little more thinking it requires. So that also will not be difficult. Just see, because I have explained it in just 2 or 3 lines. I have explained this also. No difficulty. Just think of this once again. Any doubt is there. So this is taken as the definition for refractive index. Now this definition of refractive index, just see here, very simple it is. Velocity of light in the rarer medium is higher, denser medium is lower. So this value greater by lesser. Greater by lesser, just see some examples of greater by lesser fraction. This is called as a fraction. Greater by lesser means something like 4 by 3. What is the value of 4 by 3? 1.33. So it's clearly greater than 1. But lesser by greater is what? 3 by 4? 0.75. It's less than 1. So this value is clearly greater than 1. So this refractive index defined by this equation is always greater than 1. Now this refractive index is simply called as refractive index of the denser medium with respect to rarer medium. It's called refractive index of glass with respect to air. Its value has been determined exactly as 1.5. Refractive index of glass with respect to air is defined as 1.5. So what is symbol for this now? N. Refractive index, simply N. So this refractive index is also called as what? Refractive index of the denser medium with respect to rarer medium, or simply it's called as refractive index of simple example I am giving. Refractive index of glass, denser medium is glass, with the rarer medium here is what? Air. So experimentally from these values of velocity of light in glass and air, its value has been determined as 1.5. why it comes as 1.5 already we have seen. I have given two values. Values are not important here, just for the sake of understanding I have given. Air velocity of light, you just later check it from the books or from the internet, you check it. 3 into 10 power 8. Glass it is 2 into 10 power 8. So 3 into 10 power 8 by 2 into 10 power 8 will be 3 by 2, because 10 power 8 10 power 8 will get cancelled. So 3 by 2 is what? 1.5. That way it comes. So this is the best example. Always the best example for refractive index is refractive index of glass with respect to air. Another example is refractive index of water. If you take a water or even ice block also, slight difference will be there between water and ice block, but almost same. Refractive index of water with respect to air is 1.33. So this is the simple definition of the refractive index. So very simple definition it is, no complication anywhere, but very important. It's a ratio of velocity of light in the rarer medium to the velocity of light in the denser medium. It's called as refractive index of the denser medium with respect to the rarer medium. So whatever things we are saying here are simple. So now again consider the definition of the refractive index here, how it is defined in terms of velocities of light in the rarer and denser media. Now from this definition, the actual what is called as Snell's law of refraction can be understood. It is almost same thing as the definition of refractive index, only one small point will be different. What is that point? Both will, I said, almost similar they are. So what is that point which is slightly extra point is required for what is called as the Snell's law of refraction definition? It's not called as, because it's a law, it's not called as a definition, it's called as statement of the law. So what is the statement? Now again consider the same thing. So refractive index of the denser medium with respect to rarer medium, like glass with respect to air, we have seen its value is what, how it is defined by definition of refractive index. We have seen that it is defined as velocity of light in the rarer medium divided by velocity of light in the denser medium. So it's also called ratio of velocity of light in the rarer medium to the velocity of light in the denser medium. A by B is called ratio of A to B. Division is called as ratio. So this is how it has been defined. Now one important thing is, just observe here, velocity of light in the denser medium, we have seen that refraction of light, more refraction occurs. So more refraction occurs means refractive index will be more, because refractive index has been defined like that only. If refraction is more means refractive index will be higher. So imagine that refractive index is very high. Thus automatically means that refraction or bending of light will be very high. So instead of going just straight, it's bending very much towards the normal. Then what happens now? Angle in the denser medium will become very small. So if the velocity of light in the denser medium is very small, then angle in the denser medium also will be very small. So V denser is small means angle in denser medium also will be, denser medium angle is what? What is the symbol here? Exactly speaking, it's called theta denser, but for convenience it's called as R here, because I and R are very simple. Theta denser, theta rarer, they look like two big words. Theta denser or theta rarer, they simply called as I. So these are much more simpler symbols. So I'll directly write it as, so velocity of light in the denser medium is very low means R also will be very low. So velocity of light in the denser medium is not so low but slightly higher means R also will be higher. Like that, they are somewhat directly related. So in case of velocity of light in the denser medium, we can just imagine R also, because it's somewhat directly related to this. The same way, if the velocity of light in the rarer medium is very high, then refractive index is more. Refractive index is more. Already we have seen that refractive index is somewhat directly related to the velocity of light in the rarer medium. So not only that, it also will be directly related to the velocity angle in the rarer medium. So velocity of light in the denser medium is somewhat directly related to what? Angle in the denser medium smaller. Like that, if velocity of light in the rarer medium is high, then automatically angle in the rarer medium, what is this angle in the rarer medium? I. That also will be high. So it can be proved, but this is much more easier. Always denominator, this part is much more easier here also. So if velocity decreases in the denser medium to very low value, because refraction is more means velocity decreases in the denser medium to very low value, R also will be low. So V denser is something similar to R. The same way it can be proved, but this again will not be so easy, though I have explained in just 2 or 3 lines. This also will be requiring something 2 or 3 lines, but it's even more thinking will be required. So those who are interested, you just try this. It will not be very complicated. It can be proved by a little thinking. So velocity of light in the rarer medium is higher means automatically angle in the rarer medium also can be taken to be higher. Velocity of light in the denser medium is lower means automatically angle in the denser medium also will be lower. So it can be proved that roughly V rarer by V denser, roughly we can just roughly write it as I by R. Not just V rarer by V denser is approximately we can take it as I by R, that is angle in the rarer medium divided by angle in the denser medium. Really, a scientist by name Huygens was the scientist who actually invented a very important thing. So he found out that this ratio of the velocities of light in the rarer to the denser medium is exactly equal to I by R. Not just we are just guessing that this ratio will be approximately equal to I by R, because V rarer is greater, I is greater. V denser is lesser, R is also lesser. So we just guessed that this ratio should be approximately equal to angle in the rarer medium divided by angle in the denser medium. But Huygens was a scientist. He gave a certain principle called as Huygens wave principle. So from this wave principle, he proved that exactly this ratio is exactly equal to I by R. Not even slight mistake will be there, exactly equal to I by R, but provided when I and R are very small. They are very small, they should be less than 10 degrees. But see here, what is the value of I here? Not only in this situation, normal situations, I will be not 10 degrees, it's about, this value is roughly about, if you measure with a protractor, this total angle between the normal and the surface is 90 degrees. This total angle between the normal and the surface, normal means perpendicular angle means 90 degrees. So this total angle, we can see that it's 90 degrees. So this I is approximately half the 90 degrees, that means 45 degrees. So that's how usually the value of I and R will be. I is 45 degrees, means R we already know that R should be slightly less than I. R should be how? It should be slightly less than I. So I is 45 degrees means R will be some 35 degrees, 36 degrees, 37 degrees like that. But still the values are considerably high. But when I and R are small, I and R, angle in the rarer and denser medium are small, that means less than 10 degrees or even lesser than 10 degrees, much less than 10 degrees, then only Huygens found out that this ratio will be exactly, almost exactly equal to I divided by R. Ratio means division. So this is ratio of V rarer to V denser. This is the ratio of I to R. A by B means ratio of A to B. So this ratio will be almost exactly equal to this ratio. So that's the thing. So now we are getting a new equation for refract. N stands for refractive index. Refractive index of denser medium with respect to rarer medium is already from definition. So earlier we have seen, by definition, refractive index of denser with the rarer is velocity of light in the rarer to the velocity of light in the denser medium. So that is one definition, basic definition of refractive index. Now we are getting a new equation for refractive index. So refractive index of denser with respect to rarer is nothing but equal to, it's also equal to the angle in the rarer medium divided by angle in the denser medium, or angle of incidence in the rarer medium divided by angle of refraction in the denser medium, or in simple words, angle in the rarer medium divided by angle in the denser medium. It will be equal to this ratio. So refractive index is also not just equal to this ratio, refractive index is also equal to this ratio, provided I and R are the two angles I and R have small values, less than, much less than 10 degrees. Now what if I and R values, the two angles small r and small I, what if they are big, like in this diagram, 45 degrees, I here is roughly 45 degrees, 50 degrees, 60 degrees, 70, 80, 90 like that. If I and R have big values, then also approximately it is found that not exactly now. Earlier when I and R values are small, they have small values, then almost exactly equal to this ratio. That is almost exactly equal to refractive index of denser with respect to rarer medium. So if the values of these two angles are big enough, much bigger, that means 45, 50, 60, 70, 80, 90 like that, then also it is found that roughly approximately equal to ratio of the velocity of light in the rarer medium to the velocity of light in the denser medium. Thus, when I and R are, the angles I, small I and small r are very small, then the ratio of velocities here is exactly equal to I by R. and when small I and small r values are large, the ratio of velocities is approximately equal to I by r. This is what Huygens found out from his wave principle. And another very important thing related to this particular equality is a particular operation. It's a very special operation, so it can be understood like this. The important thing about this operation is this operation is applicable only for an angle. So small I here and small r are nothing but angle of incidence and angle of refraction, or more clearly the angle in the rarer medium and angle in the denser medium. Observe the cursor compulsorily. So small I here in the diagram, it can be seen it's the angle in the rarer medium and small r is the angle in the denser medium. So now corresponding to any angle, now consider in general an angle theta. Related to this angle theta, a very special operation is defined. So that is very important here in this particular equation. So Huygens found out that if this special operation is performed on angle theta, now this special operation is called as a trigonometric operation. It's called sine operation. It's written as sine. So this operation, sine operation, when it is performed on the angle theta, it's called sine theta. So what is sine theta? What is this operation? So this operation is a regular operation in just like a regular operation in mathematics. For example, you have learned about addition operation, addition of two numbers a plus b. Next, subtraction operation, a minus b. Next, multiplication operation, a into b. Next, finally division operation, a divided by b. So similar to the division operation, so division a by b is also called as ratio of a to b. So this trigonometrical operation sine theta is also like a division operation. It's actually related to division of two sides of a triangle in which we are considering this angle theta. So more exactly this, how sine theta is exactly, how this operation sine performed on angle theta is how it is done. It will be exactly coming in another, it's actually belongs to a particular branch of mathematics. It's a particular branch, part of mathematics called trigonometry. Now, those students who are in the 10th class, so already you might have learned about trigonometry. There is no problem in applying sine theta. But refraction lesson actually it's a part of even 9th class syllabus also. In many states, or in at least in some states, in the 9th class syllabus itself, refraction is present. This topic refraction is present. This lesson refraction of light is actually present. For such students, presently just remember that sine is a particular operation which is performed on any angle theta. So theta can be anything, 45 degrees, 50 degrees, 60 degrees, exactly. Anything, any value it can have, it doesn't matter. So this operation is defined in such a way that, so very important thing is, sine theta is somewhat directly related to angle theta. Supposing you are increasing the angle theta this way, then automatically sine theta value also will be increasing. So that's the importance of this special operation called as trigonometric operation or sine operation done on theta. Now this sine operation, now just see the spelling sin. Sine really is, it's spelled like this. The full spelling is actually done like this, sine. It's read as sine, sine, like sign, signature sign, sign, like that it's read. But when it is written along with an angle theta, the letter E is actually deleted. So because it's becomes too big to write. So in short, it's written as sin, just, but still it's pronounced as sine theta only. So that's the important thing about it. So when this operation sine is performed on these two angles, so Huygens found out that so sine is performed on angle I, and also again sine operation is performed on angle R. So it's called sin I. So now the ratio I by R can be written as sin I by sin R. Then Huygens found out that again from his wave principle, exactly ratio of velocity is exactly equal to ratio of the angles I and R. That is ratio of the sines of the angles I and R. Sin I by sin R. Ratio of sin I to sin R. This equation will become an exact equation. And he found, so the important thing is here I and R need not be small. They can be large. I need not be just less than 10 degrees, like 5 degrees, 6 degrees, like that. So it can have any value, 30, 40, 50, 60, 70, 80, 90. Important thing is R will be slightly less than I. For example, I is 80 degrees, R can be some, say 8, instead of 80, I being 80 degrees, R can be some 70 degrees or 60 degrees, like that. So like that. But the important thing is, whatever be the pair of values I and R, angles in the rarer medium, just observe the diagram again, angles in the rarer medium and the corresponding angle in the denser medium. So sin I by sin R is exactly equal to ratio of the velocities in the rarer medium to the denser medium. So That's what is the final equation. So this is a very important result. This gives a second definition for refractive index of the denser medium with respect to the rarer medium. Already we have seen the first definition. So the first definition was this equation. This was the first definition of refractive index of a denser medium with respect to rarer medium. It's the ratio of velocity of light in the rarer medium to the velocity of light in the denser medium. So that's the first definition. Now this gives a second definition. Refractive index of denser medium with respect to rarer medium is the ratio of sine of the angle in air. I denotes what? Angle in air to the sine of the angle in the dense medium, or ratio of sine of angle in the rarer medium to the sine of angle in the denser medium, or ratio of sine of angle of incidence in air to the sine of angle of refraction in the denser medium. So anyway, it can be defined. So this is the second definition for refractive index of denser medium with respect to rarer medium. Now already we have seen the topic. The topic name is, just try to remember the topic name, refractive index n. So now we have two definitions for refractive index. And what is Snell's law of refraction? Now Snell's law of refraction is this second equation itself. Now this is the first very important equation in this topic. It carries 3 marks, 4 marks, even 5 marks also. So main two equations are this only. This is the first equation, which is nothing but the first definition of refractive index. This is the second equation, or second result, second important equation in the topic, which actually really is the second definition of refractive index of a denser medium with respect to rarer medium. So this itself is actually this form. When this particular equation is considered to define refractive index, this itself is simply called as Snell's law. So from this we can get the statement of the Snell's law. See here, I'm just writing. So already we have seen earlier, this is the this is the definition of the refractive index, n. So really we are considering refractive index of denser medium with respect to rarer. General symbol for refractive index is only simple n, because it's considered for a denser medium with respect to rarer medium usually. That's why denser and rarer, which medium. For example, glass and air here, glass with respect to air, or like here, water with respect to air, like that it should be mentioned more clearly. So now, what is the statement of the Snell's law? This itself is the statement of the Snell's law. So this is the second part of this particular topic, very important. So this is the statement of what? Snell's law. I have to write Snell's law here. So I'll just write it later, or else I'll just complete it faster. Snell's law in short. So this is a statement of what? Snell's law itself. Later I'll write this more clearly. So now just observe here. The ratio of sine of angle in the rarer medium to the sine of angle. A by B is what called? A divided by B can be called, or ratio of A to B. So ratio of sine of angle in the rarer medium to the sine of angle in the denser medium is equal to what? Ratio of the velocities of light in the rarer to the velocity of light in the denser medium, which is nothing but refractive index itself. But the important thing here, what is the value of refractive index? It's a constant. The reason is velocities of light in the given two media are constants. Velocity of light in air is what? 3 × 10⁸. Velocity of light in glass is what? 2 × 10⁸. So their values being velocities, numerator and denominator being constant, ratio also will be constant. So important thing here, this is a constant. That is the important thing of the statement of the Snell's law. So we can get we are getting the statement now in a simple, very simple equation. Sin I by sin R, that is ratio of sine of the angle in the rarer medium to the sine of angle in the denser medium is what? Refractive index, which is nothing but really what? Constant itself. So this ratio is a constant. So that's the important thing here. This itself is called as a statement of the Snell's law. So first part of this topic is, it's almost a 5 marks topic also. We have seen refractive index. So we have seen that it can be defined in two different ways, and from the second definition we are getting the complete statement of the Snell's law of refraction. So simply, what is the statement of the Snell's law? Now just see, it's very simple. Now the real meanings are important here. I and R are what? Not just angle of incidence and angle of refraction. The important thing is general meanings are taken here. So strictly speaking, I have to write this here. What is sin I by R? Sin I by sin R. Sin I is nothing but theta rarer, angle in the rarer medium. So I have to write it more clearly, is equal to sin theta rarer by sin theta. R is small r is what here? Theta denser, angle in the denser medium. So that way it's actually defined, the Snell's law of refraction. The ratio, when a light ray is actually passing between two transparent media, then the ratio of sine of angle in the rarer medium to the sine of angle in the denser medium is a constant. What is this constant called as? It is called as refractive index of the denser medium with respect to rarer medium. So actually I have to write here again n denser with respect to this. I have to write here. There is no place here So this is the complete meaning of this is a complete statement of the Snell's law. It is very, very simple. So whatever things we are saying here are simple, nowhere any complication is there. So this is the important thing here. Now this constant has another very important meaning. Now that's the main part of the Snell's law of refraction. Actually it's not visible here directly, but it can be easily, the meaning can be actually, the meaning was clearly explained when the law was given by the scientist Snell. So he got this law from actual experiments. He did not use Huygens wave principle. Snell got this law separately without using Huygens wave principle. He experimentally proved that sin I by sin r is constant, and this constant itself he called it as a refractive index of the denser medium with respect to the rarer medium. So what is the importance of the experiment? Now the importance of this experiment and the actual meaning of this equation can be understood from this diagram. Now just see here, sin I by sin r is constant. Now here constant refractive index is definitely a constant. The reason is already we know that. What is the why? The reason why it's constant, we know the reason. Huygens wave principle. Refractive index, velocity of light in the rarer medium by velocity of light in the denser medium, which is sin I by sin r. Really the ratio of velocities is being a constant, so refractive index definitely will be constant. So sin I by sin r is also constant. That we are getting it from Huygens wave principle. So when Snell gave this law, he really found out that sin I by sin r is really a constant. So what is the meaning of this? Sin I by sin r is constant. So he found out that now this constant means it has a fixed value. Already we have seen one simple example, two examples we have seen. Refractive index of glass with respect to air, denser medium with respect to rarer medium air is 1.5. Again denser medium with respect to rarer medium, that is water with respect to air, is 1 point. Definitely it's a constant. But whatever, definitely, so right hand side is a constant, so sin I by sin r also, left is equal to right means left hand side also should be constant. But important thing is in the left hand side there are two quantities, I and r. What are I and r here? Are their values I and r values always constant? They are not constant, they are actually variables. The reason is I is some angle made by the incident ray with the normal. What angle? This light ray here, incident ray can be incident on the, at the point, at any angle. It can be incident at 45, 50, 60, and accordingly, according to this angle, r also will be having its own value. For example, when I is having some 60 degrees, r being lesser than 60 degrees slightly, it can be 50. But when I is 80 degrees, r is found to be always just less than I. So I is 80 means it will be 70. That means I is changing, r is also. So these two are really variables. And Snell found out that experimentally. He actually changed I continuously, and he found out that he got different values of r experimentally. What is this experiment? How I is changed, was changed by Huygens, and how r is actually changed, how r is measured. This actually will be coming in the syllabus itself a little later. After 1 or 2 topics this will be coming. How to find r and how to find I. More clearly it will be coming. So Snell actually performed this experiment, and he found out when he increased I, he found out that r also will be increasing in such a way that the ratio always remains constant. This ratio always remains constant. What is the meaning of this? This simply means that when I is increased in such a way that sin I is doubled. Sin I is doubled. How can sin I by sin r still remain constant when sin I is getting doubled? Doubled means I would write 2 into. How can this ratio be constant? Then this ratio can be constant only if sin r also increases such that it also should get doubled. So when sin I is increased such that it's, when I is increased in such a way that sin I, we already know that when theta increases, sin theta increases. That way sin theta, trigonometric ratio, this particular special operation called as sin operation or trigonometric sin operation has been defined. So when I is increased, sin I increases, and if it is doubled, supposing that it's getting doubled, so the numerator becomes what? 2 sin I. So how can the ratio be constant? Only in one way it can be constant. Sin r also should be doubled. So sin r should be increasing, r should be increasing in such a way that sin r should get doubled. So numerator you write 2, this also 2 you write, and 2 will get cancelled. So ratio remains same. That is the only way sin I by sin r can be constant. When sin I increases doubled, sin r also should be doubled. Sin I increases tripled, sin r also should get tripled. Then only the ratio will be remaining constant. That means when sin I increases, sin r also will be increasing proportionately. This is called proportionate increase. When this is getting doubled, this is also getting doubled. This is tripled, this is also tripled. This is quadrupled. Quadrupled means 4 times it is increased. This also gets 4 times increased. Such that then only the ratio will be. That's the meaning of Snell's law of refraction. So that's the complete statement. So now we can understand the statement actual law, actual experiments performed by Snell. So he found out this law without using any special. Huygens wave principle came much later than Snell. So Snell got this law experimentally, but he could not prove this. Why this is correct? Snell could not prove, Einstein could not prove, no other scientist could prove it. Later Huygens, from his wave principle or his special theory called as wave theory, using this theory, Huygens actually proved that sin I by sin r will be constant. The reason is he found out that sin I by sin r is really equal to the velocities of light in the two media. Ratio of velocities of light in the two media. Velocities being constant, definitely this ratio has to be constant. That's the final thing given by Huygens. So we have done firstly Huygens wave principle because it's very easy to understand. So originally, historically, first Snell's law was discovered, and then it could not be proved. Even by Snell himself could not prove it. Only experimentally he proved that it is correct. But what is the theoretical reason? What is the reason behind that? He could not explain. Huygens, from his wave theory of light, in his wave theory of light, he gave a very special principle called wave principle. With this principle, he finally proved that sin I by sin r will be really constant. Why it is really constant? Because it's equal to the ratio of two constants. Velocities of light are constants. So constant by constant has to be a constant. So that's the thing. That's the complete information related to the present topic. So what is Huygens wave principle? All these details later you will be learning in still other classes. For example, when you go to next class, again physics continuation, you will be having what is Huygens wave principle. It's a very simple principle, but found to be very, very, very powerful principle. Even Snell's law, this particular law, Snell's law, is also very, very extremely powerful principle, which can explain almost many things in optics. And this was actually explained using Huygens wave principle. So Snell's law has been explained using Huygens wave principle. So that's the thing about the Snell's law of refraction and that is definition of the refractive index, the present topic. Now observe one small thing here. Now just observe this particular equation again. So here we have two different definitions for the refractive index of denser medium with respect to rarer medium. It's nothing but defined as ratio of, just here, velocity of light in the rarer medium. Just observe the diagram. Velocity of light in the rarer medium divided by velocity of light in the denser medium. Now this ratio itself is called as what? Refractive index of the denser medium with respect to rarer medium. The same way, now if you consider the reciprocal of this velocity of light V rarer by V denser, A by B reciprocal is what? B by A. For example, A reciprocal is, I'll just write roughly here, A reciprocal, I'll just immediately remove it also. What is the reciprocal of A? 1 by A. And what is the reciprocal of A by B? What is the reciprocal of A by B? 1 divided by A by B it will be. So it can be proved that, you just try to write this on notebook, you can just prove it easily. Reciprocal of A is 1 by A, that's how reciprocal is defined. So for example, reciprocal of 3 is 1 by 3, reciprocal of 4 is 1 by 4, that's how reciprocal has been defined. What is the reciprocal of A by B means 1 divided by A by B, it will be becoming equal to B by A. So just I have written this for convenience, for the sake of understanding. So I'll just remove this so that already so lot of rough column information has I have written here, so many things. So everything will become congested if too many things are written. For example, these vertically opposite angles, all these things, rough columns, compulsorily you must write them in your rough notes, in your rough column of the notebook. For example, you are getting this, for example, I'll make this very neat. I'll write these all the steps very clearly, but in rough column it gives the reasons actually. So reasons are most important in science and technology, or science and engineering. So without reasoning, reasoning only is understanding. Without understanding or proper reasoning, nothing can be remembered, nothing can be used also, nothing can be remembered also. So it will become forgotten, it will be forgotten very quickly. So once it is understood by proper reasoning, by proper steps, then it can be remembered for a long time, it can be applied also, it will become very useful also to understand later topics, other subjects in the still higher classes. Everything will become very simple once principles are applied. How principle is applied to different steps, how a definition is applied to different steps. So here we have one law or principle, that is Snell's law is a law or a principle, and next we have one definition, that is the definition of refractive index. So now so here refractive index of a denser with the rarer is what? Velocity of light in the rarer by velocity of light in the denser. Now we consider the reciprocal of this. What will be the reciprocal of this? Just now we have seen it will be reverse. V denser by V rarer. Now this is called V rarer by V denser is called refractive index of denser with respect to rarer medium. Like that, V denser by V rarer, that also is a constant, because constant by constant is constant. Numerator A by B is A and B are constant, means A by B is constant, B by A is also constant. Like that, the reciprocal also will be constant, but that reciprocal is called as rarer with respect to denser, that is refractive index of the rarer with respect to denser medium. So that's another refractive index. but refracting of denser with respect to rarer is greater than 1. Already we have seen 1.5, 1. The reason is velocity of light in the rarer medium is bigger than, it's greater than velocity of light in the denser medium. But if we take the reciprocal, it will become less than 1. Less than 1 values are very difficult to remember, 0.8, 0.7 like that. That's why the other refractive index, rarer with respect to denser, is never considered. Only in certain situations only, if it's useful, then only it's considered. In most of the situations, 99% of the situations related to refractive indices or understanding the behavior of light, only refractive index of denser with respect to rarer is only used. Just as we know, refractive index of glass is 1.5. This will be very, very useful, whatever be the topic or whatever be the subject. So later physics gets, when you go to still higher class, physics gets divided into different branches. For example, different branches of engineering. Electricity will become electrical engineering. Electricity and magnetism will become electrical engineering. And mechanics will become mech engineering or mechanical engineering, like that. So different branches of engineering and different branches of physics. Engineering is nothing but, engineering and technology is nothing, they are nothing but applications of science, or mainly applications of physics itself. So that's the thing here. So thus we have even refractive index of rarer medium with respect to denser medium also. How is defined means just the reverse reciprocal of this ratio. So it can be defined like this. Refractive index of a rarer with respect to denser is what? Velocity of light in denser by velocity of light in rarer. So it will be equal to sin r by sin I. Sin of I in the denser medium by rarer medium, that way. But it's not much useful. So these are the various things related to the present topic. So whatever things we are seeing here are simple. Nowhere any complication is there. Now here the statement, important thing is here, sin I by sin r is nothing but the ratio of sin of angle in the rarer medium to the sin of angle in the denser medium. I and r stand for angles in the rarer medium and denser medium. So they can also be written as sin theta rarer. So what is I, angle in the rarer medium? Already we have seen. So I is the angle in the rarer medium. Just observe the diagram. I is the angle in the rarer. It can also be written as theta rarer. And r is the angle in the denser medium. It's also been written as what? Theta denser. So that way also it can be written. So here in brackets it can also be written more clearly as equal to sin of theta rarer by sin of theta denser. That way also it can be written more clearly. So here the rarer medium we are taking it as air, or even vacuum also can be taken. Denser medium we are taking it as glass. So in most of the situations, rarer medium is usually taken as air or vacuum. But in certain situations, real life situations, sometimes the rarer, many such situations also, many situations exist in which the rarer medium need not be air, it can be water. For example, a glass block immersed in water. So surrounding the glass block, which medium is present? Water is present. That way rarer medium need not be always air. Certain situations, special situations, other media also can be present. Now, but the simplest thing, we are usually present only with air as our surroundings. So any denser medium, the surrounding rarer medium can be taken directly as air. So this is a very, very special refractive index of a denser medium considered only with respect to air or vacuum, where air or vacuum is the rarer medium. Now such a refractive index of any medium with respect to vacuum, so more exactly it's called vacuum, because air and vacuum, their velocities are almost same. Already I said it before, 3 × 10⁸ meters per second, but really that is the value of velocity of light in vacuum. In air its value will be slightly decreasing, so it's not exactly 3, also 2.999 like that. Even if the exact value is taken also in air, because air is slightly more denser compared to vacuum. Vacuum density will be 0 because there is no mass in vacuum at all. So air has slightly more density, so velocity slightly decreases. So exactly speaking, so the best refractive index is refractive index of any medium with respect to vacuum, because any medium has to be more denser than vacuum only compulsorily. So such a refractive index of any medium with respect to vacuum is simply called as absolute refractive index. It is simply called as absolute refractive index. So the absolute refractive index, I'm just writing it in a new page on the right hand side of the screen. So this is the next small topic. It's simply called as what? Absolute refractive index. So I'm writing in short, later I'll write this more clearly. Now this is a small topic important for 2 marks. It's not a separate big topic, It's same thing as what we have already seen. So what is absolute refractive index? It is nothing but what? It is the refractive index of the any medium with respect to vacuum. So here, by the definition of refractive index, or by the statement of the Snell's law, we already seen that sine of the angle in the rarer medium, theta rarer, divided by sine of angle in the denser medium. So exactly speaking, what is this here? Sine I divided by sine R. That is what we have seen more clearly in the actual statement of the Snell's law. So sine I by sine R, which is nothing but sine theta rarer by sine theta denser, is what? It is simply equal to what? It is equal to velocity of light in the rarer medium divided by velocity of light in the denser medium. Simply it's called as what? Refractive index of the denser medium with respect to rarer medium. So here the rarer medium, we are taking it as what? Vacuum. So rarer medium, we are taking it as vacuum, exactly speaking, or roughly it can be taken as air also. So the denser medium, we are taking it as any medium. Any medium will be only denser compared to vacuum. So any medium can be taken here. Then what is happening is the equation now can be written as sine theta vacuum divided by sine theta of that particular medium. Any medium will be only denser compared to vacuum. So that medium, directly we can use the same word, medium. MED stands for medium. It's equal to velocity of light in the vacuum. Now velocity of light in vacuum is always fixed value, roughly 3 × 10⁸ meters per second. So exactly speaking, it will be 2.999 like that, many recurring. So large number of, that is uncountable number, infinite number of digits will be coming. So with any accuracy it can be determined. So because it's difficult to state that 2.99 right or 2.999 like that, it's written roughly as 3 × 10⁸ meters per second. So this velocity of light in vacuum, it's a constant value, because it's found that all colors of light in vacuum, they travel with this constant velocity. That's why it's called as a universal constant. So this special velocity of light in which medium now here? Rarer medium is what here? Vacuum. This velocity of light in vacuum, so V vacuum should be called. So because it's a universal constant, it's taken, it's written as C. So now divided by velocity of light in that particular medium. So in that particular medium, any medium is only denser compared to vacuum. So this is simply called as what now? It is simply called as refractive index of the that particular medium with respect to which medium? With respect to which is the rarer medium here? Simply vacuum. So I'll just write this here more clearly. Velocity of light in that particular medium, that is denser medium, with respect to rarer medium is what? Vacuum. Now always any medium, this particular refractive index of that particular medium with respect to vacuum, it is simply called as absolute refractive index. So absolute refractive index is nothing but refractive index of any medium with respect to always vacuum. Medium is glass, means refractive index of glass with respect to vacuum. So medium is water, means refractive index of water with respect to vacuum. So the rarer medium is never changing here, it's always fixed vacuum. So in the absolute refractive index, whenever absolute refractive index is values are considered, it can be written as refract n medium with respect to vacuum, because it's always absolute itself means with respect to vacuum. So vacuum need not be again and again written. So in short, it's written as what? Simply refractive index of the medium. So there's nothing but what? With respect to vacuum only. When rarer medium is not mentioned, means it's fixed that it's taken as vacuum. It's understood that it's taken as vacuum. So this is the simplest symbol for absolute refractive index. So the general symbol for absolute refractive index is what? N medium. Second medium is not mentioned here. Only that particular medium. Second medium is, we know, it is vacuum. So that is actually not mentioned. So this is a simple symbol of the absolute refractive index. So what is the best example for this? We know the best example already. So the best example is absolute refractive index of glass. That means refractive index of glass with respect to air or vacuum is what? Already we know it is 1.5. Next, absolute refractive index of water. So from examples, actually the meaning can be understood or remembered more clearly. So what is absolute refractive index of water? 1.33. It's also with respect to air or vacuum. So these are the two simple examples of absolute refractive index. Now consider the general refractive index. So absolute refractive index, always it is understood that it is with respect to vacuum. But if the rarer medium is not vacuum, some other rarer medium is taken, then such a refractive index is called as relative refractive index. It is opposite of absolute refractive index. Absolute refractive index means the second medium, rarer medium is what? It is vacuum. But if it is not vacuum, some other rarer medium means that's called a relative refractive index. So whatever equation, earlier definition we have seen, just see the earlier definition, this one. For Snell's law statement we have seen, or the definition of the refractive index we have seen. That's always nothing but refractive index of any denser medium with respect to rarer medium. That itself is called as relative refractive index. So relative refractive index is not a new thing. So relative refractive index now directly can be this refractive index, whatever the definition of refractive index we have seen, that itself is nothing but the relative refractive index itself. So from this now we are getting, after absolute refractive index, what is called as the relative refractive index. So I'm just writing that here. So this is the absolute refractive index we have seen. So next topic is called as the relative refractive index. This is not a separate definition, it's same thing as what we have seen earlier, refractive index itself. So relative refractive index. So what is the relative refractive index? It's nothing but refractive index of, so definition is very simple. So these are not separate topics, that's why I'm writing the side headings, just roughly I'm showing. They are not very useful for marks. So just 1 mark it carries because it's not a separate definition. So see the earlier topic, 3 marks, 4 marks and even 5 marks also it can be asked. Absolute refractive index to some extent it's 2 marks. So relative refractive index, it's not a new topic, so it's just even if it's asked also just 1 mark it will be asked. What is the definition? It's the refractive index of any medium with respect to any other medium. Any medium with respect to any other medium. So what is the example, best example for this? Refractive index of a denser medium with respect to any rarer medium. So this is one simple example. And any other example? Now just see here, already we have seen one example. Just as refractive index of denser with respect to rarer is defined, the same way refractive index of a rarer with respect to denser also is defined. How it is defined we have seen roughly, but it's not useful much. But still this is also called as, because some other medium with respect to some other medium means refractive index of any medium with respect to some other medium is defined as what? Relative refractive index. So this is also called as, by definition it's also called as, it's also an example of relative refractive index. So that's the simple meaning of the relative refractive index. Now the important thing is, what is the relation between relative refractive index and absolute refractive index? A very simple relation can be obtained between relative and absolute refractive indices. Now for this, just observe here this absolute refractive index definition. Now just see this part. The absolute refractive index of any medium, that means with respect to vacuum it is, any medium, n medium, how it is depending upon the, on what factors it is depending upon. Just see here, it is mainly related to the velocity of light in that medium. Because whatever velocities we are seeing, what is traveling in the rarer medium or denser medium? Light is traveling. So whatever velocities we are saying is nothing but velocities of light only in the medium. Numerator is what? Velocity of light in vacuum. Earlier, just earlier in the definition, just 2 minutes back only we have seen this. Now just observe here, when we are considering the absolute refractive index of any medium, it is entirely, because C is a universal constant, velocity of light in vacuum is constant, never be changing. When the medium is changing, for example from glass, if we are considering absolute refractive index of glass or absolute refractive index of water, when we are changing the medium, what is changing is denominator only is changing. Now if you are taking a very dense medium, light travels very slowly. That means velocity of light in that very dense medium will be very low. So when the density of the medium is very high, velocity will be very low. When velocity is very low, what happens to the refractive index? It will be very high, and denominator decreases means value will be value of the ratio. Ratio means the n only here. So value of the ratio or value of the refractive index increases to a very high value. So just observe here once again, it's very simple, not difficult. So in a very dense medium, so for example glass is more denser than air. Glass is more denser than air, even denser than even water also. You take a glass block and put it in water, it sinks inside water. If you are taking such a very dense medium, velocity of light in the dense medium is very low. So refractive index will be very high. So a more denser medium will have higher refractive index. A more denser medium will have higher refractive index. That's why glass more denser than water. See how its refractive index is higher than water. So this is another very important thing that can be obtained here. So this is a special note point. So what is the note point we are getting here? Very special. So refractive index. It is directly related to what? Directly related to density. The higher the density, the higher is the refractive index. Directly related to density. Somewhat directly related. Directly means once one increases, the other also will increase. Inversely means one increases, the other will decrease. But it is here directly related to the density. The higher the density, the higher is the refractive index. So that is another very, very important thing that can be observed in the definition of the absolute refractive. The definition you see, it's very simple, but it is so many things, applications the small, very simple definition has. Many things can be understood from the very simple definition. Now, what is the relation between the relative refractive index and the absolute refractive index? Now, this can be understood by a very simple thing. So, now consider the relative refractive index. So, refractive index of a denser medium with respect to a rarer medium. So, how it is defined in terms of the velocities of light? Already we have seen that. Just see here, try to remember. So, refractive index of denser medium with respect to rarer medium is what? Velocity of light in the rarer medium by velocity of light in the denser medium. So, previous topic in the definition of refractive index we have seen this. Very simple. Refractive index of denser medium with respect to rarer medium is what? Velocity of light in the rarer medium by velocity of light in the denser medium. So, applying that here, so what can be obtained is just here velocity of light in the rarer medium by velocity of light in the denser medium. So, I'll just write this as, I'll just make a small adjustment here. I'll write this as, this is A by B. So, I'll just write this as A by B. A by B can be written as, so A numerator by denominator. I'll write this as 1 by denominator, I'll write B denser divided by 1 by V rarer. It's something like A by B is what? 1 by B by 1 by A. The reason is here 1 by V denser by 1 by V rarer. 1 by V rarer you take to the numerator, it will become V rarer by 1. So V rarer by 1, again when you multiply, we'll get back again V rarer by V denser. The same thing we'll be getting. So just think of this, it will not be difficult. It can be understood easily. So this way it can be written. Now what I'll do is, now important thing is, what is required here is relation between, very simple thing. This is also not a separate topic. All these are actually very small things, applications of the main topic which you have seen. Relation between absolute and relative refractive indices. What is the relation between absolute and relative refractive indices? How to get that? So now we have a relative refractive index here. Try to bring absolute refractive index into the equation. Then we'll get the relation. But what is absolute refractive index? Try to just remember. Just now we have seen. So absolute refractive index of any medium is what? Just remember this. Absolute refractive index of any medium, N medium, is what? Velocity of light in vacuum, C divided by velocity of light in that medium. So absolute refractive index entirely depends on the velocity of light in that particular medium. Any medium, absolute refractive index is what? It is inversely related to the velocity of light in that medium. So numerator only constant will be there. Absolute refractive index of glass is what? C by V glass, velocity of light in the glass. Absolute refractive index of water is what? N water. Absolute refractive index of water is what? C divided by velocity of light in water, V water, like that. So any medium, glass means here we have to put glass, water means here we have to put water, kerosene means absolute refractive index of kerosene what? Here we have to put kerosene. But important thing is numerator C will be there. Now just with the help of this particular equation you can get the simple relation. Now here you see here, in order to bring the absolute refractive index here, you multiply the numerator and denominator with C, this way. Then what happens? C divided by V denser. What is C divided by V denser? Nothing but absolute refractive index of denser medium, C divided by V denser. So C divided by V medium is what? Absolute refractive index of that medium. C divided by V glass is what? Absolute refractive index of glass, like that, from the definition of absolute refractive index. So just see that. Any doubt is there, just put the video to a pause and then observe this. Always the important thing is the steps should be understood clearly. Even if it takes 1 or 2 minutes also doesn't matter. So we directly are applying the definition of absolute refractive. Velocity of light in vacuum, constant velocity of light in vacuum divided by velocity of light in any medium is nothing but absolute refractive index in that medium. So this numerator is now what? C divided by V denser, nothing but absolute refractive index of the denser medium. So N denser. And what is the denominator here? C divided by V rarer. C divided by V medium is nothing but what? Absolute refracting index of that particular medium. What is the medium here? Rarer medium. So nothing but absolute refracting index of the rarer medium. Whatever be the rarer medium, whether it's water or kerosene, any rarer medium. So that is what is coming here. Just observe here. So therefore we are getting a very special relation. So relative refractive index of any denser medium with respect to any rarer medium is simply coming as what? The relative refractive index of denser with respect to rarer is nothing but absolute refractive index of denser by absolute refractive index of rarer. So this is another very important equation what we are getting. So this is a very important equation. It should be by hearted. Now earlier already we have seen very important equations. The definition of the, that is actual definition of the original definition of the refractive index of any denser medium with respect to rarer medium, and the Snell's law statement. This is the Snell's law statement, including this also. Both these are almost the same because there is nothing but a constant. The same thing is written here. So this or this together is written as the second result. Very important thing. So both belong to the 3 or 4 marks question. That is the this topic, 3 or 4 marks topic, or even 5 marks, refractive index and Snell's law of refraction. Now next we have seen the absolute refractive index definition. Just see here this one. Absolute refractive index definition we have seen. This is the definition of absolute. See the side heading, absolute refractive index. And next we have seen relative refractive index, simple meaning. And next now we have seen the relation between relative and absolute refractive indices of two particular media. Now just observe here what is the importance of this. Now one certain very simple thing, one very new point can be observed here. Now what is that new point? Just see here. Now I'll just this is what is actually very important here. I want this equation and the present equation which we got now, they should be compared. So what I'll do is I'll reduce this. I'll just do one thing. This I'll bring it here. That should be visible here. Actually I am putting it here. This is our present topic, relation between relative and absolute refractive indices. Now compare this with the other equations which we got earlier. So the first equation, just see here, this is the first equation and this is the second equation. Both these are called as second equation. First equation is definition of refractive index, which we have already seen. Okay, this is actually the first equation which you have seen, and this is the second equation actually. Okay, just observe here. The present topic is this. I am putting this in the left hand side. Now compare this. Now you see here the definition of refractive index of denser medium with respect to rarer medium. Just see here, in terms of velocities of light, you see here denser with respect to rarer. First medium is what? Denser medium. Second medium is rarer. But here first in the numerator what is coming? Second medium is actually coming in the numerator. And first medium, denser medium, is actually coming in the denominator. So there is an inversion here. Denser with respect to rarer is what? Rarer by denser. Even this is also same thing. What is this here? What is sin I by sin R? Sin I by sin R is what actually? Sin theta rarer by sin theta denser. Just observe this carefully. I'm just writing this here itself so that though it's looking congested, that's the meaning here. This sin theta rarer by sin theta denser, though it's not looking very clear, but still the importance can be seen very clearly. You see here sin theta rarer by sin theta denser. That's the meaning of actually sin I by sin R. That's the real meaning of sin I by sin R. Don't always remember it as angle of incidence and angle of refraction. Angle of incidence is which medium? Rarer medium. So the sine of angle in the rarer medium by sine of angle in the denser medium. The same ratio it is, see here. Rarer by denser is what? Denser with respect to rarer. So there is an inversion here. Refractive index of any denser medium with respect to rarer medium. Whether it is expressed in terms of velocities of light in the rarer and denser medium, there is an inversion. Denser with respect to rarer is rarer by denser. Again, denser with respect to rarer is what? In terms of angles, rarer by denser. But important thing now is absolute refractive, that inversion is not there. You see, denser with respect to rarer is what? Denser by rarer only. That's the thing here. So there is no inversion here, so that's why it's very much more easier to remember. Refractive index of any denser medium with respect to any rarer medium is what? Absolute refractive index of denser medium by absolute refractive index of rarer medium. So there is no inversion. Using this any pair of media, the refractive index, the relative refractive index can be calculated. For example, we already know that refractive index of glass is what? Absolute refractive index of glass 1.5. Absolute refractive index of water is what? 1.3. 1.5 by 1.3 we'll be getting it as something like 1.1, like that. That will be the relative refractive index of glass with respect to water. Glass with respect to water we never saw. Only glass with respect to air we have seen separately. Glass with respect to air we have seen separately, and water with respect to air we have seen. What is then how to get glass with respect to water? This is the only formula. This is the simplest formula to get glass with respect to water. So that way refractive index of any denser medium with respect to any rarer medium can be easily determined, provided we know the absolute refractive indices of that two given medium. So that's the importance. So there is no inversion here. That way, this because of the direct relation, denser with respect to rarer is what? Denser by rarer. Easily can remember. Even this is also not difficult to remember. The reason is inversion is, we just know that there is an inversion. Denser with respect to rarer is what? Rarer by denser in terms of velocities. Angles it is rarer by denser. Tan theta rarer by tan theta denser. So even this is also not difficult to remember. That way all the formulae are very simple and very important also. See here, this also. Inversion is there. In the basic definition, inversion is there. And final result which we got here, relative refractive index and absolute refractive indexes, there is no inversion. So that's the thing what we got. So nowhere any complication is there. Everything here we can see that it is very simple. So now again, considering a small thing here, so whatever things we are seeing here are simple, nowhere any complication is there. Now just observe one small thing. So now using these two results, another very simple result can be obtained. So this is nothing but this very simple result is actually a very important form of the Snell's law of refraction. So previously we have seen the basic form of Snell's law of refraction. From this, by applying these two particular results, the last two equations, combining them, we can get this new form or different form of Snell's law of refraction. So it's called a different form of Snell's law. So this is also actually not a separate topic. It's useful only for as a 1 mark question, but very useful for from the understanding point of view. So I'm not showing this as a separate big topic. Now just observe here, we'll just consider the relative refractive index of again a denser medium with respect to rarer medium. So we have seen that when it is expressed in terms of the velocities of light or in terms of the angles in the denser and rarer medium, there is an inversion present. So denser with respect to rarer is what? Sine of angle in the rarer by denser. So that way we have seen that it's a inversion is there. Denser with respect to rarer is what? Rarer by denser. First denser, next rarer. Here first rarer, next denser. So inversion is there. But when the relative refractive index is expressed in terms of absolute refractive indices, inversion will not be present. Denser with the rarer is what? Denser by rarer. Absolute of denser by absolute refractive index of rarer. So it is very simple. That's what we have seen in the last two equations. So now from these two we'll get a very simple thing. Now just cross multiply this last two steps of the equation. Cross multiplication. So n rarer into sin theta rarer. So what we are getting is absolute refractive index of the rarer medium into sine of angle in the rarer medium is equal to n denser into sin theta denser. So n denser into sin theta denser. That's what we are getting. This simply means that when the light ray is actually passing from rarer into denser medium, in the rarer medium angle is what? Angle made by the light ray with the normal is what? Theta rarer. So in the rarer medium absolute refractive index is n rarer. So once the light ray is going into the second medium, that is the denser medium, we have seen that in all the previous cases light ray going from rarer into the denser medium. So what is happening is we have seen that angle made in the denser and rarer medium will be different. That means angle is changing. Next, velocity of light is changing. Next, medium is also changing. That is refractive index is also changing. So when the light ray is passing from initial rarer medium into the final denser medium, refractive index is changing. Refractive index is actually rarer, it's lesser. Denser refractive index, we have seen that it is increasing. And angle is what is happening? Decreasing. Initially rarer, it is greater angle, and finally denser, lesser angle it is becoming. So when the angle decreases, what is happening? Refractive index is increasing, but in such a way that what is happening to the product of refractive index and a sine of the angle, this product initially and finally it is remaining same. This is very, very important. So angle, when the light ray is passing from rarer to denser medium, refractive index is changing, theta is also changing, even velocity also is changing. But important thing is, many things are changing, density is changing. But when we consider refractive index and angle, though they are changing in such a way that their product is remaining same. When refractive index is increasing, angle is actually decreasing, such that the product of refractive index and angle is remaining same. So this is written as simply n, product of n and sine theta is remaining the same. So it's written as constant. Constant means same. So this is called as the final form of the Snell's law of refraction. Now the final form is a very, very important form. Whenever a light ray passes from one medium, one transparent medium into another transparent medium, always though n is changing, theta is changing, absolute refractive index is changing, theta is changing, the product of n and sine theta will be remaining the same. Now based on this, a very important consequence will be actually coming. What is that important consequence? Means it can be understood from the actual, that is a diagram. So now I'll just move this to the side so that the diagram will be visible, original diagram. I'll just try to see the original diagram. This was the original diagram. So see here, this is the result we got, a different form of Snell's law. N sin theta is constant. What is the importance of this? So whenever light ray is passing from one medium into another medium, so n is changing in the two media. N is what? Absolute refractive index of first medium and the second medium. So n sin theta is like Boyle's law, PV is equal to constant means P1 V1 is equal to P2 V2. Like that, n sin theta is equal to constant means n1 sin theta 1 is equal to n2 sin theta 2. n1 is the first medium, say rarer medium. So theta in the first medium is what? Theta rarer, or I. In general we can call it as theta 1. So in the second medium refractive index we call it as n2. Angle can be called as what? Theta 2. So n1 sin theta 1 is equal to n2 sin theta 2. So whatever be the two media, whenever light passes from one medium into another medium, always n into sin theta in both the media will be the same. It doesn't matter which media. Now we'll take the reverse. So till now we have say apply this in the reverse situation. Now initially this is theta 1 n1, theta 2 n2. Already because of Snell's law applicable, so light ray is bending in such a way that exactly it's taking an angle theta 2. When the initial angle is theta 1, it's when bending in such a way that it's exactly taking angle theta 2 such that this equation gets satisfied. That means n1 sin theta 1 is equal to n2 sin theta 2. Now what if the light ray goes in the reverse direction? Now if the light ray is going in the reverse direction, I'll draw the diagram like this. Just observe here. I'll just draw the diagram like this way. So this is n1, initial medium. I'll take it. So initial medium we are taking already take it as n1 and n2. So we'll again use the same symbols. N2 sin theta 2. When it's going into the second medium, it is what? N1. What should be the angle theta 1? Exactly, because it should satisfy which equation? This equation. Try to remember. It should satisfy which equation? N1 sin theta 1 is equal to N2 sin theta 2. So N1 sin theta 1, when it's going into the second medium, N2 sin theta 2. So now when it's taking the reverse path, how will be the light ray refracting into the first medium? In such a way that the equation gets satisfied. How can the equation be getting satisfied? Only if the angle is again the same theta 1. Just observe this carefully. It should be again the same theta 1. Again same theta 1 means it exactly takes the same path. So if a light ray is taking a path PO between initial and final points, then if it starts in the reverse direction, it again goes back along the same path PO in the opposite direction. Exactly it goes back. So this is very, very important. It's called reversibility of light. So see here, I am not explaining much. Directly we are taking the help of the final form of this Snell's law of refraction. Based on this, what we are getting is, just see here, any doubt is there, just play back this 1 minute playback, you try to get this, very easily it can be understood. So n1 sin theta 1, n2 sin theta 2. If The light ray is going from N2 to N1, second medium to the first medium. N2 sin theta should be equal to N1 sin theta 1. That's possible only if this angle is again theta 1. That means the light ray should go exactly along the same path in the opposite direction. This is called reversibility of light. So if light travels along a path between 2 points, say from P to 2 points, initial and final points, then light can exactly take the reverse path also. That's called, its path is said to be completely reversible. So this is called as reversibility of light, or principle of reversibility of light. The path taken by light between 2 points, any 2 points, say P and Q, is can be completely reversible. So that's a very important, it's said to be one of the most powerful properties in optics. Though it appears very simple, but it is not a separate principle. It is directly a consequence of the Snell's law of refraction, especially the final form of the Snell's law of refraction. The final form also is not completely different. It is obtained from the initial form only. Just by little modification we are getting this, but this is found to be practically useful. Especially it's giving the very important principle of reversibility of light. So that's the thing. So what we are getting is a new principle called as principle of reversibility of light. So this is also not a separate topic, principle of reversibility of light. So this will not be carrying any marks in the exam, because it will never be asked in the exam. But many complicated things in nature can be understood with the help of this very simple principle. So these are the various things related to the Snell's law of refraction. So all this, just see here, lot of notes is there. All these notes should be taken very clearly. So for example, this topic, everything, I'll just keep everything very neatly. I'll just make this very neat. So these actually, it comes under a note point actually, principle of reversibility of light. All these things I'll just give very neatly, so that so now see here, all many values I have written. They appear a little congested. I'll make them very neat without changing anything as it is. I'll make them very neat. In the next frame I'll be displaying it. And then you can take the running notes, because the topic is completed. Immediately the running notes should be taken. Either you should note it in the classwork book which you are preparing for the exam, using for the preparation of the exam, or you can just take the printout. So at the end of this, immediately near this video itself, I'm putting the copies of this clear copy of this entire running notes. You can download also, and without writing you can study directly from the download copy also by taking the printout. Another important thing here is, so from the principle of reversibility of light, so the path taken by light ray between the 2 points P and Q is completely reversible. So either the light ray, if the light ray goes from P to Q along this path PO to Q, then again it can exactly take back the same path in the reverse direction, that is QO to OP. That's the important thing here. So now the important thing is, supposing the light ray is going the downward direction, that is from the rarer to the denser medium. So initial angle is I, we are calling it as a theta 1, so it takes theta 2. So for an initial angle theta 1, it exactly takes the angle theta 2 in the second medium. So satisfying the equation n1 sin theta 1 is equal to n2 sin theta 2. But in the reverse direction also it satisfies the same equation. So n sin theta in the initial medium will be equal to n sin theta in the final medium, and it's going in the reverse direction. So if it's taking theta 2 angle here, it again has to take back theta 1 angle. So whether the light ray is going from this medium to this medium, that is the first medium to the second medium, or second medium to the first medium, a given pair of angles is fixed. Theta, for given theta 1, it has to be exactly theta 2, and for the same theta 2, it has to be exactly theta 1. So the symbols, the values are not changing. That's the important thing here. So now theta 1 and theta 2 are called as I and R. So while going downwards, if the angle is I, initial angle is I, then the final angle should be R. And while going in the upward direction, that is from denser to rarer medium, if the initial angle is R, it has to be again back I. That's the important thing here. So now if you apply this in the regular equation for the Snell's law, just observe the equation for Snell's law. Now remember this, if the initial angle is theta 1, it is theta 2. If the initial angle now, if it's theta 2 in the reverse direction, it has to be theta 1 again. So if the initial angle is I in the downward direction, for the downward direction of the light ray traveling, if it is I, it is for corresponding to I, if it is some value R, then in the reverse path corresponding to the same value R, it has to be exactly the same value I again. So the values are not changing. Due to this reason, whether the light ray is going downwards or upwards, very important thing is the same symbols I and R are used. The same symbols I and R are used for the angles in the rarer medium and the denser medium. Angles in the rarer medium in the denser and the denser medium. The same symbols I and R are used. What is the importance of this? Importance is now apply this in the regular Snell's law equation. This is the Snell's law equation. Just we have already seen. So refractive index of denser with respect to rarer is what? Sine of angle in the rarer medium divided by sine of angle in the denser medium. So in terms of I and R, it is sin I by sin R. So this is applicable. So always refractive index of denser medium with respect to rarer medium is for glass with respect to air or vacuum. It has a fixed value. Already we have seen it's 1.5. So because this refractive index of the denser medium with respect to rarer medium is fixed value, and we are using this particular formula, this is applicable whether the light ray is going in the downward direction or upward direction, that is from air into glass or glass into air. In both the cases, the pair of values of θ1 and θ2 are fixed. Due to this reason, the symbols for the angles in the rarer medium and denser medium are also taken as fixed. Now what is the meaning of this? The meaning is very simple. So I, we took it as angle in the rarer medium, R we took it as angle in the denser medium. Always angle in the rarer medium is denoted by the same symbol I, and always angle in the denser medium, that is glass medium, is always denoted by the same symbol R. Whether the light ray is going denser to rarer, that is rarer to denser or denser to rarer, same symbols are used. Now what is the speciality of this? Speciality is very important. Now if we consider this angle as the angle of incidence and this as the angle of refraction, when the light ray is going from rarer to denser, definitely this is true. But if it's going from denser to rarer, angle in the denser medium we are taking the same symbol R, and angle in the rarer medium we are again taking the same symbol I. But now they can't be called as angle of incidence and angle of, that is angle of refraction and angle of incidence, because when it's going denser to rarer, this is the incident medium, denser medium is the first medium, so this should be the angle of incidence and this should be the angle of refraction. So that's the meaning of I and R here. But still the meanings are definitely changing, but the symbols are not changing. So many textbooks follow this. So there is no confusion in this. Important thing is only simple. Same symbols I and R are used in the rarer and denser medium. Rarer, this is I is the always the rarer medium, R is always the denser medium. Now just check the definition of refractive index of a denser medium with respect to rarer medium. It is defined as what? Already you have seen the definition. It's the ratio of sine of angle of incidence in the rarer medium to the sine of angle of refraction in the denser medium. So, but this definition is applicable. We can find the refractive index for both the directions of the light ray because of the principle of reversibility of light. But when it's going in the reverse direction, when the light ray is going from rarer to denser medium, this definition is applicable. But denser to rarer medium, we can't call this as angle of incidence. That's why in the definition of Snell's law of refraction, angle of incidence should be avoided and angle of refraction should be avoided. They should be simply called as angle in the rarer medium and angle in the denser medium. No complication arises then. So many textbooks follow this. So simply it's defined as ratio refractive index of denser with medium with respect to rarer medium is what? It's the ratio of sine of angle in the rarer medium to the sine of angle in the denser medium. Even we can use this also. Sin I by sin R is much more simpler, but we should not take it as angle of incidence and angle of refraction. They will be, this can be called as an incidence and refraction only in the downward direction. For upward direction, this will be really the refraction, and this will be the incidence. So it's better not to use the words angle of incidence and angle of refraction. Simply they should be called as angle in the rarer medium and angle in the denser medium. So always, in general, most of the textbooks follow this notation. Whether light ray is going from denser to rarer medium or rarer to denser medium, angle in the rarer medium is always taken as I, angle in the denser medium is always taken as R. So these are another very simple thing to be remembered. So this is the, so observe the cursor compulsorily. So this is how the running note has to be written. So refraction, so carries only 2 marks, only definition. So next you see the refractive index. So these are 3 marks and 4 marks topic, as I have all explained in the class just a few minutes back. So refractive index, or it's also called Snell's law of refraction. This is how the running notes has to be written. It's coming to, so about this much. So this is a diagram and little definition, small definition. And next see on the right hand side of the page. So this is the continuation of the definition of refractive index equation. So it's simple, just as I have explained it is. And next, how the definition, from the definition of refractive index we get the Snell's law of refraction. So that is what is this particular page. So next after this page, next second page you see. So there is no problem. So one way of taking the running notes is directly copying it from the video itself. You just mm, put the video to a pause and then take down the entire notes. And even better way is I'm actually giving the link of downloading all the 4 pages. All the 4 pages, very clear pages. They can be downloaded from the link. If you just download from the link in this particular video. So just below the title of the video, the link is actually provided. You can download all the 4 pages, and then you can download it in the system or in the phone, and then slowly you can entire notes, all the 4 pages you can copy down in the notebook. And another even better way to save time is take the printouts of all the 4 pages. So this need not be again written in the classwork. That way some time can be saved. So that is another way. So whatever is convenient to you, it can be done. So but the important thing is whatever topic you have listened to on a particular day, immediately the entire running notes according to the marks it has to be prepared. For example, I'll just show the next page. So this is 4 marks, 3 to 4 marks carrying, and even 5 marks also I said it can carry. So entirely up to the end of this answer, up to the end of this page statement, it should be another 3 lines comes into the next page actually. So up to this statement it should be fully written. So next second page you see. So this is the second page. So another say this is the end of the 5 marks or 4 marks or 3 marks answer, definition of refractive index and the Snell's law of refraction. Next you have some note points. They'll not be used. Note points will not be useful for marks, but they are very useful for understanding and solving different kinds of problems, especially problems. They'll be very useful. Next, absolute refractive index of a medium you see. So it carries only 1 mark. So learn only definition plus equation 1. That's all. Nothing more is required. Entire explanation will not be required. So just see that this is the definition and equation 1. This is the equation. That's all. Nothing more is required. And examples you see, they're actually examples are very good for understanding. So you can remember the examples also. They are simple examples. And next, see the page number 3. So this is the page number 3. Relative refractive index. Another 1 mark question. So according to the marks only they have to be learned. 1 mark means just learn only the definition. That's all. Only definition, nothing more. Examples, if just for the sake of understanding, they will be useful. But important thing is definition. That's all. That's sufficient. So next thing is relation between relative refractive index and absolute refractive index. This is the running notes of that's what carrying only 1 mark. You see that means only learn only the final equation below. So entire explanation, derivation is not. This is a small derivation, but derivations are very powerful for understanding, for increasing the understanding. They are very, very good derivations, but because it carries only 1 mark, just final equation is sufficient. Just see how many marks it's carrying, 1 mark. Just what is the relation between relative refractive, this is the relative refractiveness, and this is the absolute refractive index of denser medium and rarer medium. So this is the relation, just 1 equation is sufficient. So next page 3, after this is page 3. So next page number 4. This is the page number 4, just see here. The different form of Snell's law. I said we have already seen this is a very, very important form of Snell's law. It's actually sometimes called fourth equation for Snell's law. You can just check the numbers I did not put because this carrying a 1 mark, only the equation is sufficient. So learn only the final equation. That's all. See here again, this derivation is again very, very useful. Without derivation there won't be any meaning at all. So only for the sake of understanding and for the sake of meaning, derivation you have to go through, and but for the examination you have to remember only the equation, and for problems also this equation will be very useful. And next 1 note point, and the statement of the principle of reversibility of light. And this is a diagram we have already seen during explanation. Few minutes back we have seen. So this carrying any marks, you see, no marks. There's a note point carrying no marks, but a very, very powerful principle. Already we have seen this particular principle. It's very, very one of the most powerful principles in optics. Actually, this is said to be one of the most powerful principles in optics. It's not a separate principle. It comes from Snell's law. So this is the principle of reversibility of light. So this way, so compulsorily immediately after the listening to the class, immediately you have to complete the running notes in the classwork in your notebook, whichever notebook you are maintaining for physics, and then or you can just download it and take the printouts, but keep the hard copy should be with you, either printouts hard copy, that is hard copy, or in the notebook completed by copying from the downloaded running notes.